Okay, so it is time. So welcome everybody. My name is Michael Barton. I'm going to chair this session on geometry processing. So good morning, good afternoon, or good evening, depending from wherever you are joining us. And we have two talks in this session. But before introducing the speakers, I just say a few words about this Zoom environment, because most of us are not familiar with it. So I would like to ask you during the talks, all of you except the speaker, to keep your microphones muted, because otherwise this is kind of annoying and disturbing. And also you can, if you have a question, there is a feature in the participants panel. You can raise your hands to signal that you have a question, even though I would prefer, if you have a question, to wait until the end of the talk. And yeah, that's basically it. And also as a warning, in the morning sessions, we had a problem that the Zoom somehow crashed unexpectedly. So hopefully this is fixed by now. But if not, I would just ask you to be patient. And if it happens again, to reconnect. Yeah. So if the Zoom crashes and the session disappears, I will restart the session and you would be able to rejoin it. So hopefully the issue is fixed already. So okay, so this is it from my side. So now let's move to our first talk. Yeah, so the first talk is gonna be by Zipeng. Yeah, I apologize in advance. My pronunciation of Chinese names is very bad. So Zipeng, hopefully I didn't make too much harm to your name. And Zipeng is going to speak about Dirichlet energy of Delaunay meshes and intrinsic Delaunay triangulations. So Zipeng, now I would like to ask you to share your screen with us and unmute your microphone, and the stage is yours.
Hello. Hello, everyone. I'm Zipeng Ye.
Yes, we do hear you. Perfect.
Okay. Hello, everyone. I'm Zipeng Ye from Tsinghua University. It's my pleasure to have a talk to you. The topic of the paper is Dirichlet energy of de Broglie meshes and intrinsic de Broglie triangulation. I introduce my paper from four aspects: preliminaries, holistic cotangent harmonic interpolation, relationship of Dirichlet energies on de Broglie meshes and intrinsic de Broglie triangulations, and applications and results. At first, we introduce preliminary of our works. We will introduce the definitions of Dirichlet energy, intrinsic de Broglie triangulations, and de Broglie meshes. Dirichlet energy is to measure the smoothness of a function on mesh. For triangle T and a function f on T, the Dirichlet energy is defined as follows. That is 1/2 of the integral of nabla f in T. Using the finite element method for triangle meshes M and a function f on M, the Dirichlet energy is the following. The weighted sum of the square of difference of each edge. The weight is 1/2 of cotangent alpha ij plus cotangent beta ij. Alpha ij and beta ij are the opposite angles of eij. We will introduce the definition of intrinsic de Broglie triangulations. A is a triangle mesh M, and D is its IDT. Firstly, the IDT's vertex set is the same as that of M. Secondly, every IDT edge is a geodesic path in M. The green edges are geodesic paths. Thirdly, for each interior edge, the local Denali criterion is satisfied. Lastly, Dirichlet energy of IDT is no more than that of the original mesh. We will introduce the definition of Denali meshes. A is a triangle mesh M.
Ich gucke nur zu jetzt gerade.
And C is its DM. Firstly, DM is a spatial type of IDT which has some new vertices. The green vertices are new vertices. Secondly, DM are triangle meshes. Thirdly, DM has more vertices than the original mesh, whose function value are obtained by interpolation. We propose a novel interpolation scheme for DM. That is holistic cotangent harmonic interpolation. DM has new vertices, and F on M is undefined on them. We have several naive interpolation schemes, such as barycentric interpolation and cotangent interpolation. However, they both can't reach the global minimum of Dirichlet energy. We propose a novel scheme, holistic cotangent harmonic interpolation, which can reach the global minimum of Dirichlet energy. Given a two-manifold mesh M with M vertices, a scalar function f on it, and a Denali mesh DM of M, which has M plus n vertices, the function values fm plus 1, fm plus 2, dot fm plus n of the n new vertices are unknown. The following linear system of equations has a unique solution to length, and the solution reaches the global minimum of Dirichlet energy. The linear system has n equations for each new vertex. The weighted sum of its neighbor edges equals 0. The linear system is nabla DE equals 0 for n unknowns. The form is X equals B, and we will show A is positive definite. We only need to show xTax is greater than 0 and xTax equals 0 if and only if x equals 0. We have the weight of each edge is positive because of the local Denali condition. So A is positive definite. Therefore, the holistic cotangent harmonic interpolation can reach the global minimum of Dirichlet energy. The linear system is a sparse system. There are many existing methods to solve the system. Use Jacobi iteration to solve it in n square time. We will show the relationship of Dirichlet energies on DM and IDT. The conclusion is Dirichlet energy of DM with our interpolation scheme is no more than that of IDT. For proving that, we construct an interpolation scheme, incremental barycentric interpolation. For n new vertices of DM, we incremental add them, denoted by mi, the IDT of m plus I vertices. Spatially, Mn is the DM. Incremental barycentric interpolation is the following. Firstly, we compute IDT of the mesh M and compute a DM with n new vertices and m original vertices. At each time, we insert a new vertex Vi. The value of the new vertex Vi is computed by barycentric interpolation on IDT. Energy is not changed. Then we compute the IDT of the m plus I vertices, which is Mi. Energy does not increase. Repeat it n times, we get the DM. After incremental barycentric interpolation, we have Mn is DM and this EFIDT is greater than EFN on DM, is greater than EF star on DM. F star is our interpolation. We will show some results. This is the Dirichlet energy of the origin mesh, IDT and DM with different interpolation schemes. Dirichlet energy of DM with our interpolation scheme is no more than that of IDT. These are results of texture mapping. We have texture coordinate in original vertices, and the values of new vertices are obtained by interpolation. The texture mapping with our interpolation scheme is more smoothly than that with barycentric interpolation. These are results of geodesic interpolation. We compute geodesic distance in original vertices, and the values of new vertices are obtained by interpolation. The geodesic with our interpolation scheme is more smoothly than that with barycentric interpolation. That's all. Thanks.
Okay, thank you, Zipeng. Thank you very much for your presentation. So we have time for a couple of questions. So if somebody wants to ask a question, there is a raise hand button in this participants list. If there is no question, then maybe I will start with one. So Zipeng, you were showing the timings. There was this table where you were showing the times of your interpolation and barycentric interpolation. So is it really that slower than barycentric interpolation? Is it correct that the barycentric interpolation is by several orders of magnitude faster? And if so, what is the reason why your scheme is that slow there?
Because the time cost of barycentric interpolation is O(n) or O(m plus n). Our interpolation takes O(n) square time.
I see. So there is this complexity analysis, and this is something that you cannot fight much against, right? or is there any idea how to speed up your method? Because as far as I understand, your method is a lot slower, but it produces more accurate results. Yeah, is it like this?
I think the speed up method of solving a linear system can help our interpolation. But I'm not very good at how to solve the linear system.
I see. No, but there can be some speed ups, but probably one cannot do that much with this complexity. Yeah? If your complexity is quadratic in n, and barycentric interpolation is linear or superlinear, this cannot be beaten probably. Okay, another question. If not, maybe I will have another one. So in your algorithm, you solve a linear system, and you have this matrix. Could you please, maybe you said that, but I kind of lost it. How do you guarantee that the matrix is regular?
The linear system is number d equals 0 for the n unknowns fm plus 1 to fm plus n. It is for each new vertex, we have equation for all its neighbor edges, the weighted sum, the difference between the two
Fi and Fj are function values at the vertices, right?
Yes.
Okay.
The function value on the ith vertex and the function value on the jth vertex.
I see. And okay, so go one slide down, please.
The proving has many details. We just show the idea of the proving.
Okay, I see. I can look it up in the paper then. Okay. Thank you. So are there any other questions from the audience? If not, then we will thank Zipeng once again, and maybe we can wait for 5 more minutes, because the next talk is supposed to start at 12:25 of our European time. So thank you, Zipeng. You can stop sharing your screen. I would ask.
Okay, thank you.
I will ask Luming to start sharing his screen, but I suggest to wait 5 more minutes, just in the case that somebody was planning to participate for the second talk. So yeah, we will wait now for actually 4 more minutes, and then we start.
is it possible to have some advice about general use of Zoom? I'm not very familiar with it, and I'm confused about the calendar. I'm not sure whether my poster presentation is today or tomorrow, and I'm trying to get an answer. But I'm also not sure of how to show any viewers the pictures from my presentation. So could we take this few seconds for you to give me a little bit of advice?
Okay, so Jack, regarding the poster session, you need to check the program. The program is here. I'm going to copy it to our chat.
There's a conflict because I've had from the organizer a date of a time of 5 o'clock today, but on the calendar it says that it's tomorrow. So there's a confusion between the two.
Let me see. The poster session, as far as I know, was on Thursday, but there is poster 2 that is
about FACE, Fabrication Scouting events.
I'm sorry, can you please say it again?
I guess, Jack, you're referring to Fabrication Scouting, right?
The phase one, it's about a randomizer.
It's today, 5 o'clock UK time.
It is, okay, but I'm really very dumb about Zoom. I'm not a mathematician, I'm an artist, and I'm struggling to get this, but I want to show pictures on mine. Do I just go to share and then pull
yes,
my
yes, you will be able to share your screen as soon as you will be on the session, because when you're on the session chair can give you co-chair privileges, and then you can share your screen.
Right, yeah, you cannot do it now, Jack, because you don't have
I realize I can't do it now. I'm just trying to be sure that I know what I'm doing a little bit before the time.
Okay, I see. But yes, you will get co-host, right? So you will be allowed to share your screen, and there is a green share screen button in the middle of the panel of your Zoom window. So you just click on it, and then actually Zoom gives you the option to choose what particular program on your computer is going to be shared. Yeah? So you are not sharing the whole screen, but you can say, I want the Zoom to share Adobe, for instance, if you have your presentation in PDF.
For instance, if I have some artworks put on my screen ready,
yeah.
and I want to click on a particular picture, then if I click on that picture, do I drag it over to Zoom, or will it automatically come in the screen?
No, it will give you, the Zoom, once you click on this share screen option, it will give you actually what kind of program, if it is some PNG picture, so it will select some viewer, and it will give you the option to share the particular picture that you like.
Okay, as long as I can get some guidance, because I'm a little bit worried. It's only a 5-minute presentation, so I want to make sure that the 5 minutes is usefully employed.
No problem. Actually, once the session ends, we can check it. I can give you the rights, and we can try it out if you like.
Sorry, I missed that.
After this session ends, we can try it out. Yeah, I can give you the co-host rights, and you can practice it if you like.
That would be ever so helpful. What you get in touch with me?
Sure. Yeah. After the session, we can do that.
That would be wonderful. I'd be so grateful.
Sure. No problem.
Sorry to interrupt.
You are welcome.
Thank you for your help.
So great. So now it is time to move on. Our second speaker is Luming Sao. Again, I apologize for my pure Chinese pronunciation. And Luming is going to speak about quasi-geodesic distance fields. And yeah, the slides are ready. So please, Luming, the stage is yours.
Okay, thank you. Can you hear me?
Yes, we do hear you. Perfect.
Okay. Hello, everyone. My name is Luming Cao from Shandong University, China. I'm going to present our work, Computing Smooth Quasi-Geodesic Distance Field with Quadratic Programming. Geodesic on a mesh is the shortest path between 2 points on this mesh, In this work, we focus on computing the distance from the source vertex, like this blue dot, to every other vertex on the mesh. The resulting distance field is smooth and approximate to the geodesic distance field. There are currently many exact geodesic algorithms, such as MMP algorithm, improved CH algorithm, and the VTP algorithm. They maintain wavefront on mesh edges and propagate it across the faces in a Dijkstra-like sweep. Some approximate methods, such as faster matching method, Dijkstra's algorithm, SVG algorithm, and the DGG algorithm, seek a trade-off between precision and time. However, the resulting distance fields of exact methods and those kinds of approximate methods are only continuous but not smooth, and so there exist many sharp Caspers. There are also some algorithms could obtain smooth distance field, such as commute distance, diffusion distance, biharmonic distance, and heat method. But the first three have very poor accuracy. Although the heat method is much more accurate, may still have a serious precision issue for geometrically and topologically complicated models. So by comparing the distance fields computed by exact method and the heat method, we can see that heat method smoothes the sharp Caspers, but also significantly changes the shape of isolines and other regions. So there is currently no algorithm can balance precision and smoothness. Our method computes a smooth approximate distance field by minimizing a standard quadratic programming, and we use only one parameter to balance accuracy and smoothness. Due to the flexibility of the formulation, our method has many advantages. For instance, it can be easily extended to multimodal data, such as point clouds and tetrahedral meshes, and is robust to tessellation and noise. It can obtain defect tolerant geodesic on meshes with hosts. It also supports user-specified constraints, which cannot be easily handled by the other approaches. So our work is mainly based on the following two works. Firstly, Lancier proposed to use the shortest path on the graph to approximate the geodesic. And the more reasonable the graph, the more accurate the approximation. And secondly, the Laplacian energy is a classical smoothness energy used for data smoothing. Our method combines the above two methods. Dijkstra's algorithm is a classical method of calculating the shortest path on a graph. It can be formulated into a standard linear programming. The capital letter D in the objective function is a scalar field. Each element represents the distance from source point to target point, and the equality constraints enforce the values at source points to be 0. We can obtain a distance field by maximizing the optimization problem. From blue to red, the distance is increasing. But in order to add the smoothness term to the objective function later, we need to replace the maximize problem into the minimize problem. In this case, m is an arbitrary constant. Now this is the optimal solution, but we notice that the scalar field is conversed. The values of points near the source are larger than those far from the source. And that's because for this minimized problem, M minus D reports the real distance field. Then introducing Laplacian energy into the objective function can smooth the distance field. Now, lambda is a balanced parameter. A large lambda tends to approach the exact geodesic distance, while a small lambda is able to emphasize the smoothness requirement. However, the first term in the objective function is quadratic about D, while the second term is linear, which cannot guarantee the parameter is invariant under the change of model skills. And so we promote the second term into a quadratic form. This is the final formulation of our method. Now M should be set to a sufficiently large constant to guarantee the variables are non-negative. Generally, the Hessian matrix is positive definite, so this definite. So this standard quadratic programming that can be solved by many mature solvers. The effect of smoothness term mainly has the following three aspects. Firstly, it can smooth the distance fields. On the left, the distance field is computed without smoothing, while on the right, it is smoothed with Laplacian energy. You can see that the sharp Caspers have disappeared. So this might be nice to a few of applications need smooth distance fields. Secondly, the input data generally has noise. We use the smoothness term to get a noisy resistant solution. In this experiment, we add a huge amount of random noise to the mesh. When computing the distance field, we lower the balance parameter to suppress noise. By mapping the resulting distance field back to the original model, we can see that it's not very far from the distance we expected. Thirdly, introducing the smoothness energy can improve the accuracy of our algorithm. I will explain it in detail. The left picture shows the shortest path computed on the edge graph. The edge graph is constructed only by vertices and edges of the triangle mesh. And the right picture shows a geodesic path. It can be seen that the shortest path is not allowed to cross the faces of the mesh, thus resulting a zigzag walk that's far more wiggly than the exact geodesic path. So you can imagine that the shortest path distance field must be far from the exact geodesic distance field. We present these two kinds of distance field on the Keaton model. On the left is the exact geodesic distance field, and in the middle is the shortest path distance field. The isolines of shortest path distance field have obviously oscillations, and the mean error is 6.53%. On the right is the smooth shortest path distance field. The isolines looks more smooth and more close to those of the exact distance field, and the mean error reduces to 5.13%. And so the smoothness is helpful to improve accuracy. And so to further improve accuracy, we need to build a reasonable graph, which is very important for graph-based method. In this paper, we use a simple trick when constructing the graph. For each vertex, we connect it with its k-order neighbors. When k greater than or equal to 2, we use geodesic distance as the length of edges instead of straight line distance. It can be seen that the accuracy is significantly improved, but more running time is required. So we use the two-order neighborhood in the default setting. Our method can be applied to multi-model data such as triangle meshes, point clouds, and tetrahedral meshes, as long as the Laplacian energy and the graph can be defined. So on the choice of the balance parameter, we take lambda equal to m divided the square of h in our experimental setting, where h is the average edge length, so that m is a constant invariant to model scales. We can see that a smaller m tends to a more smooth result. So we generally take m equal to 10 to the power of -3 to balance accuracy and smoothness. We compared time and accuracy with heat method, dexterous algorithm, faster matching method, and the VTP algorithm. The best speed or accuracy statistics are highlighted in red. It can be seen that our method is much more accurate than the other three approximation algorithms, but our algorithm doesn't have an advantage in speed, which is due to the fact that solving a large-scale quadratic programming is time-consuming. However, it takes 87 seconds when the number of phases amounts to 500,000, which can be tolerated in most applications. This figure presents the other methods that aim at getting a smooth distance field. It's clear that commute distance, diffusion distance, and biharmonic distance are far from exact geodesic distance. The heat method has a better approximation than them, but our method achieves the best trade-off between accuracy and smoothness, only smoothing the sharp cuspers, but not changing shape of SO lines and other regions. Next, I will briefly introduce two applications of our method. One is defect-tolerant geodesic computation. On the left are the distance fields computed by exact approaches and most approximation methods with Newman boundary condition. In the middle are the results of biharmonic distance. They are all sensitive to open boundary. While our algorithm can naturally support the defect-tolerant geodesics by using the Hessian energy proposed by Stein et al. To replace the Laplacian energy. Thus, the distance fields computed by our method are not seriously affected by open boundaries. Since our formulation is based on an optimization-driven framework, it's easy to support various user-specified constraints. When users specify additional constraints, it basically implies that the original inequality constraints may be destroyed. So we need to introduce the relaxation variables. The new equality constraints are user-specified. In the following, we shall exhibit the flexibility of our methods using two examples. This is another way to compute defect-tolerant geodesics. Users can specify the distance values at some special points to correct the distortion of SO lines near open boundaries. In this example, we assume the distance values at the two red points are corrected. The distance field in the right picture is modified by these two new equality constraints. It looks much better. Seems like the SO lines are totally not affected by the boundary. The rationale behind it is that the smoothness term can guarantee a natural transition everywhere in the distance field. And when a model that's supposed to have symmetry is asymmetric, for example, the two wings of the bird in the left picture have different shapes. Under this case, even the source point is selected on the symmetry axis. The resulting distance field cannot inherit the symmetry of shape itself. We can enforce the distance as the two wings tips to be equal so that to yield a more meaningful distance field in the right picture. So we propose a quadratic programming-based framework that's able to seek a trade-off between accuracy and smoothness using a unique balance parameter. It can be easily extended to point clouds and tetrahedral meshes, and is flexible to compute defect-tolerant distance fields and support user-specified constraints. However, there are also some limitations of our method. One is that the algorithm doesn't have an advantage in speed. Another is that the distance computed by our method is not a metric because it doesn't satisfy symmetry and triangle inequality. There are still a couple of things we'd like to do in the future. We need to speed up our algorithm and further improve accuracy. So that's all. Thank you for listening.
Okay, thank you very much, Romain, for a very nice presentation full of beautiful and colorful pictures. So I'm wondering if there is some question from the audience. Yes. Oleg is asking. So
the question is, you're using, well, apparently using quite good triangulations for your meshes. Have you tried find geometric distance on mesh with bad triangulation, like with degenerate triangles, or where triangles are of very different size and so on?
Pardon, could you speak slower?
Oleg, could you please rephrase your question?
Yes, have you tried your method on meshes with bad triangulation? Degenerate triangles, triangles of different size, and so on.
Luming, your input are only kind of beautiful Delaunay meshes. The question was, what happens if you have a lot worse input? If you have meshes that have some obtuse triangles, yes, or some narrow triangles. So have you tried your method on this kind of input?
Yeah, our method is not sensitive to the triangulation.
Well, then maybe this is why the question was asked, because on very many examples that you have shown, the meshes are kind of nice meshes. Yeah. So you have also tested it on ugly meshes.
Yeah, even the mesh with low quality, we can still get an undesirable solution.
Okay. There is another question in the chat. Slide 22, probably. Why is the distance not symmetric for a symmetric model? Can you throw some light on that? So, Luming, if you could go to slide probably 22. The question is that for symmetric model.
Oh, this?
Yeah, no, this is not symmetric model, but so maybe this donut, double donut, slide 25. One slide above. This one, yeah, this is symmetric, right? And the question is saying, why is the distance not symmetric for a symmetric model? Well, this depends on the point of origin, I would say, if I understand it correctly, and if we are on the correct slide. Yeah, so now, of course, it is not. If I may answer instead of you, and if I understood correctly the question, of course, the position of the source, let's say, the point from which we measure the geodesic distance is put in some non-symmetric position of the object. So I'm not sure that I have followed the question and if I answer it. So there is another question. You compare to the heat method. However, last year the vector heat method was introduced. Would you suspect to still perform better to this state-of-the-art method? Yeah, so the heat method of Keenan, Crane, and colleagues probably. Vector heat method. So if you could comment on vector heat method. Is it clear? The question, there was another question from the audience saying that there is also a vector heat method. So if you are familiar with that and if you have tested. against this vector heat method?
Heat method is not that accuracy because it's very sensitive to the tessellation. It even can't get a desirable result on medium quality meshes or complicated models. So that's why it's the error of heat method is very high.
Okay, I also see once again Oleg's hand up, but I'm not sure if it was from the previous question or if Oleg wants to. Okay, so the hand is down now. I was actually wondering about this smoothing. So to me, what is the motivation for smoothing? If you have this geodesic distance, and even if you are in 2D and you have offsets, to me, cusps are something that is natural. If you increase the offset distance, it depends on the curvature of the curve and how far you get. You might get cusps. And what you were saying is that you would like to get rid of the cusps of these isocurves. So is it really because to me these cusps are, even though they may not look that beautiful, they say some information about the surface and about the curvature of the surface. So I'm wondering why this smoothing parameter lambda is needed, and why do you study it?
Yeah, our method could be a much accurate when we build a more reasonable graph. So it could really approach the exact geodesic distance. However, heat method heat method is some property for the heat method to use the unit norm of the gradients, because the gradients at the sharp cuspers is not unit, so it's not very property for heat method to. So that's why heat method and cannot get a desirable solution for complicated models.
Okay, never mind. So is there any other question from the audience? I guess this is just a comment, and yeah. So if there is no other question, I would like to thank both our speakers, and yeah, I wish you to enjoy the rest of the conference and the next sessions. I'm happy that our Zoom did not crash during our session. So thank you for participating, and goodbye. So Jack, do you hear me? Svayunas was sending a link.
I do hear you. It looks as though I might have to do a PowerPoint presentation, but my idea was in 5 minutes simply to show some pictures and talk to them, because the idea is very simple that I'm putting over, and 5 minutes isn't very long. So I may not need a full PowerPoint presentation to do a 5-minute talk. Okay,
so Jack, for your rehearsal, there are actually two options. There is this link that Svayunas has sent you into this chat, and in that link you have a meeting room where you can practice your rehearsal, or you can do it now. It is fine with me, so I can give you the if you want to, you can try it out. Yeah, I will give you the co-host rights now.
Okay. How are you going to give me that? Are you going to put it on the screen?
So now you can see it in this participants panel. If you click on participants, there is a list of people who are joined to this session. And you should see now with your name a red dot that is blinking, and this signals that you are co-hosting the session. So now you should be able to share your screen with us.
Click on participants like that.
So if you click on the green button, there is a share screen green button.
Yeah.
It should give you several options of what program on your computer should be shared. Yeah, you may have several running applications, and the Zoom is asking for a specific application that you want to share. So if your presentation is in PowerPoint, you click on that.
Well, all I was thinking was all I need was access to a few pictures to speak about the problems associated with the pictures. Because I'm talking about the philosophy of perception in art.
I see. But do you have these pictures? In what format do you have these pictures?
No, I've got them on my paper, but I don't think there's time to go through the paper. But I can put some pictures on my screen and drag them across.
Well, if you have a hand-drawn pictures, you need to scan them for us, because otherwise the Zoom will not.
I've got a PDF I could try now.
Yes. So now in your share screen option, you are giving rights to Zoom to share your Adobe Acrobat or whatever PDF viewer you have.
But I've got to get on my screen, the white screen. How do I get the picture onto the white screen? I mean, can I drag it and drop it on?
Well, if you click on share screen, there should be an option. There should be a window that gives you an option to share your screen with a particular application. So now we see your screen. Now we see your background picture. Yes, and now we do see the pictures.
I see. So that's the machine I'm going to talk about.
Okay.
A randomizer. And I'm simply going to relate that to the pictures before and after, and what the aesthetic problem is in terms of graphic chaos, which is my topic.
Yeah. Okay. Whatever. So now we can see this picture that you intend to show, and if you have more, you just switch them, and that's it.
Because I drag them over. Did I get that right? You drag them over to the screen for share.
Yes. Yes.
Okay. Well, that's very helpful. What I'm seeing at the moment, I'm trying to put a picture behind my screen, but my screen is black. I'm not able to share the video with you at the moment. I'm not sure how to do that.
And if you want to share a video, you probably have to stop sharing, and again say that you want to share again. You have to stop sharing this session, or maybe now we are sharing your whole screen, so maybe you can play the video nonetheless. So now if you click on the video that you have,
no,
maybe
it isn't that, it's and my face isn't showing on the screen, so it would be better if when I'm talking to people, my screen at the moment under my name is blank. It's black.
well, this is up to you. You can switch your video on. It is, I guess, better to show your face, but this is up to you. But the most important is the video. So if you want to play a video and you have it on your desktop and double click on it, we should be able to see it. Now we see your, so there is some.
That's the whole paper.
The whole paper, yes.
Yeah.
This is also what we can see.
I can scroll up that, but I will bring some large pictures. But it would be nice to be able to talk face to face with people, and I'm still not sure how to.
And then you have to have Then you have to have a camera. So do you have a desktop computer or?
Yes, I have a big iMac with a camera on it, but I'm not.
Okay, so then there are two buttons, mute and stop video. In the bottom left corner of your Zoom window, you have mute and stop video options. And so you have to click on it to start your video.
There should be start video button.
There should be stop and start video button.
I've got stop video and start video.
Yes.
Start video. But there's nothing coming on the screen. My screen is still blank. This is what's confusing me. I'm sorry.
I see. This is strange. Yeah. So but you see the mute and start and stop video button in the panel, bottom panel of your Zoom application.
That's it. All I've got is, can you still see my screen?
Yes,
Yes.
we do see this machine that is now covering the face of the cat. And now you are dragging some PDF. Now you are dragging the PDF from the right.
Very helpful, but I want to talk to people. I mean, it's a very short philosophical statement, and I can't get my picture.
Okay, so do you see start video button at the bottom line?
No, I've just got a black screen here.
But okay,
video.
Jack, if you in your Zoom window that you have this bottom panel, and the bottom panel from the left starts with your microphone picture. Okay, now this.
now you stop sharing screen. Okay.
I guess now Jack managed to click on end button. So end button obviously works. Yeah. So that's it. So yeah, hopefully we have at least helped him to start sharing his screen, and yeah, with the video it is probably better, but not
Okay, maybe
essential.
he should just like show that paper with pictures, because I think he will lost in all these files.
Yeah, I can imagine probably for people with certain age, this teleconferencing is a nightmare. Yeah, so
Yeah, but I guess they have still in that session enough time, so maybe people will be patient, and it's okay.
Yeah, I hope so. Okay.
So thanks for the session, and see you.
Sure. See you.